They might vary the shape of the cross section, or they might do washers or whatever. So we'll work a bunch of different types. I mean, I intentionally left this for today because we would have a long time and we can practice this quite a bit. Because I'll be shocked if it's not on there. I can't remember the last time that there was a year that it wasn't on there. So, okay, so we're going to integrate, and we're talking about S, right? So we're talking about from K to 2, right? So from K to 2, that's how our squares are stacking up. They start at K and they go all the way to 2. So we're still going to use those as our bounds. We're going to integrate from K to 2. And then we're going to integrate the area of those squares. So the area of a square is side squared. So you got to figure out how long the side of each square is. The side of each square is not constant, right? The bigger this distance is, the bigger the square is. And the smaller the distance is, the smaller the square is. So the side of the square is going to be an expression. And what it is whatever this length is. So how would I find this length between these two curves? I'll give you a hint, we've already done it one. It just should be top curve minus bottom curve, right? Because the distance to this curve from the x-axis is the y value, right? Or it's the actual equation for that curve. And then the distance to this curve is its y value. So we're just looking for the difference between those two, right? So we're just going to do top curve minus bottom curve, and that'll be the side of the square. So remember, the top curve was f and the bottom curve was g. So we're just going to do f of x minus g of x. So we stacked up our squares from K to 2, perpendicular to the x-axis. If they had said perpendicular to the y-axis, you would have to use the y values. And I don't know if they've done any of those in the last few years, but if they have, we'll go over one in a minute. But because we're perpendicular to the x-axis, we use the x's, so K to 2. And then we do top curve minus bottom curve, x minus g of x. And then we square it. Don't forget to square it because you're doing the area of a square, which is side squared. On my calculator, I'm going to do 4, 2, K to 2 of f1 of x minus f2 of x squared dx. So make sure you put the f1 minus f2 in parentheses and then put the square on the outside, right? Because you want the side to be squared, the whole thing. 1.283. So if they had said the cross sections were semicircles, then you would integrate 1/2 pi r squared. If they had said cross sections are isosceles right triangles, you would have done 1/2 base times height, and the base and the height would have been the same. So basically 1/2 the base squared. If they told you to, I can't think of other shapes. Triangle. If they did a rectangle, sometimes they'll do a rectangle and it'll have like a constant height. So they'll say, rectangles with heights of 3. So you would do the base times 3, and the base would be f minus g. So they may vary the shape, but it's integrate the area of the shape, whatever shape they tell you the cross sections are. And so the key will just be to figure out, in this case it was the side of the square, or the side of the triangle, or the radius of the semicircle, or the base of the rectangle, or whatever. And it's top curve minus bottom curve. So this was worth 2 points, I think, on this part. Let's see here. Yeah, no, 3 points. 3 of 9 points. So 2 points for the setting the problem up, and 1 point for the answer. So 7 points of those first 2 parts. Right, so that was above the average on the question. All right, and then on part C, part C is not very common. I hadn't actually seen a question like this before. It's not hard though. What would have been hard is just that your teacher would not have gone over a question like this, because it's not typical. So let's look at C. Let H be the vertical distance between the graphs of F and G in region S. So we actually already talked about that vertical distance in region S. That was the F1 minus F2. That was the F minus G. Right? Find the rate at which H changes with respect to X when X is 1.8. So the rate at which H changes means the derivative of H when X is 1.8. So basically we just need to write an equation for H and then tell the calculator to take the derivative of that at 1.8. It's really not a very hard part of the question. Like I said, it would have just been that it was not familiar to you because this is not something they have asked in the past. So we're going to say that h is the distance between f and g. So it's f minus g. So we're looking for the derivative of h at 1.8. So what we can do is we can tell our calculator to take the derivative of f minus g at 1.8. And so I'll show you how to do that. So remember, f is in f1, g is in f2. Do menu calculus number 1. The derivative at a point. And where I want it to take the derivative at is at 1.8. Right, that's the value they gave you in the problem. And then the function I want it to take the derivative of is f1 of x minus f2 of x. Right. So I want it to take the derivative of f1 minus f2 at 1.8. f1 minus f2 is the vertical distance of two curves in S. They had said in R, we would have done f2 minus f1, because remember the two curves switch places in R. But we're in S at 1.8, negative 3.812. Negative 3.812. So this was worth 2 points. Yeah, so knows that you need to take the derivative of h, and then the answer. So negative 3.812 or 3.11. Alright, so let's look at another one of these area between curves problems. So that was the 2015 number 2. Let's look at 2014 number 2. 2014 number 2. And here we'll get to see the washer method. It's on part A. I'll show you the washer method on the page. Alright, so it says let R be the region enclosed by the graph of f of x and the horizontal line y equals 4, as shown in the figure above. Find the volume of the solid generated when R is rotated about the horizontal line y equals negative 2. So y equals negative 2 would be down here. So they're going to take this area. Have y'all ever seen those party favors or party decorations where it's you know what I'm talking about? Yeah. Where you kind of open them up and they open them up like this. It's so sad. Alright, so it starts off as this flat shape, and then you take that shape and you rotate it, and it makes like this solid figure. What I used to before it got switched to my drawer for you. Alright, so that's the idea here. We're going to pick it up on this edge right here, and we're going to spin it around this axis right here. So on the outside, because the outside edge is flat, on the outside it's just like a cylinder. Right? But on the inside, you have like this weird, trying to picture what it would be like. Hard to. Oh, and actually the cylinder would go the other way. It would be like this. And it would have this weird like shape taken out of the inside. Something like that. Oh, sorry, like that. Right. Sorry. Yeah, kind of like a, there'd be more space between these. I didn't do a very good job spacing it out because there would be all of this space, and then on the other side, right, it would be like that. It's a picture. How did you get that? Yeah, so it said that they were going to rotate it around the line y equals negative 2. So it would be like y equals negative 2 is going to be the middle, and then they're going to pick this up and rotate it around that. So it spins around that way. It's not incredibly important that you can picture what the shape would look like. I'm just trying to show you on this one so you kind of understand the formula a little bit better, so it won't be so much like you're having to memorize another formula. You'll kind of be able to reason your way through it. But if you notice, on the other problem, the cross sections were squares. When they do cross sections, they can use any shape they want. But when they do rotations to make the volume, the cross sections are always circles, right? Because if you rotate, right, you rotate in a circular motion, so it's always a circle. So they're not going to tell you circles. You just have to know because they're forming the volume by rotating that you're going to use the area of a circle. And in this case, there's two types of problems. There's what are called disks, which would be if there was no space between the area that you were rotating and your axis of rotation. They never give disk problems because they're too easy. Because on a disk problem, it's a solid shape, and so it only has one radius. They're going to do washers. And the reason we have to do washers, does everybody know what a washer is? It's like a disc with a hole in the middle. Have you seen washer before? Have you ever played the game washers with the washers at the hole inside of them? Or like if you do anything with construction, sometimes you'll put a washer under a screw so it doesn't like go through your wood or whatever. Ever seen that before? That's what a washer is. A washer is just a disc that's had a hole cut out of the middle. So they call this the washer method because if I slice this into discs, all of the discs would have a hole in the middle. Right? Does that make sense? So it's like stacking up a whole bunch of washers and creating this volume. And so what we have to do is we have to integrate the area of the washers. And the washers all have two radiuses. They have an outer radius and they have an inner radius.
Oh, wow. So the whole thing is a washer?
It's a bunch of washers stacked up. Yeah, a bunch of little washers stacked up. Why do they pick washers?
Yeah.
Well, what other shape would they use to make the volume though? Cause
Not realistic.
Yeah, it's just a way like because before calculus, the only shapes you could find volumes of were like regular shapes. I mean, they have to be solid. They have to have certain dimensions that you can measure. Calculus lets you find volumes and areas of all kinds of weird shapes, but they rely still on those shapes that you can find areas of. So even though this is a weird shape that I could never find the volume of, if I break it down into familiar shapes that I can find the area of, I can use those areas to add up to a volume. Does that kind of make sense?
Yeah.
It will blow your mind if you start thinking about the people that came up with this. Like, how would you look at a really weird shape and go, oh, I'm going to slice that into discs with holes in the middle, and then I'll find the area of each disc, and then I'll add that up. I'll add in a third dimension and find the volume of that weird shape. And then how do you know that you're right? They use like submerge it in water or whatever and figure out. You know, I don't like to think about it because it makes my head hurt. So here's the washer method. To find a volume by washers. Right? So this would be a problem when they ask you to find the volume of a solid that's created by rotation, rotating something around something else. You're going to integrate the outer radius squared minus the inner radius squared. Okay, so that's what it means. Outer radius minus inner radius. Oh, and the pi. Sorry, we need a pi. Pi r squared, right? That's the area of a circle, pi r squared. You gotta have pi. Don't forget the pi. And so for the washer method, there are two radiuses squared. There's the outer radius squared and the inner radius squared. So we're integrating the area of a circle, which is pi r squared. We just happen to have two radiuses because we have a washer. Okay, so on this problem, the outer radius would be from the center of your solid, right, which is the axis of rotation, right? They told us we were rotating around the line y equals -2. So from here to the outside edge of your area. So what is this distance from this axis of rotation to this outer edge of the area that I'm rotating? 6. Yep. It's a constant 6. That's the nice thing about the problem. This problem is they gave you a horizontal line as one of your boundaries. So it made this outer radius a constant 6. Yeah. So if you read the problem, it says we have this region R that's enclosed by the graph of f and the line y equals 4, and we're going to create a volume, kind of like, have you ever seen one of these party things? You have like a flat shape, and then you rotate it, and it makes like a volume. Have you seen one of those before? So that's what we're doing with this, is we're taking this flat shape and we're rotating it around this line to create a volume. It's basically like a cylinder, but it's got this weird kind of hourglassy shape cut out of the middle. And we're trying to find the volume of it. Does that make sense? So we're trying to figure out what the two radiuses are.